Hello and welcome to this 5th edition of the Euronaval Talks. For those of you joining us for the first time, this is a series of events that was organized by Euronaval team to make sure that we keep the link with each other, that we keep the conversation going between 2 iterations of the show, of the trade show that will happen in Paris this year in November. We hope that you are going to enjoy this talk with us today, and if you do, don't forget that there are 4 other ones that you can go and have a look at in replay on the same website. And for those of you joining us again, we are really happy that you're enjoying this series, and we hope that you'll enjoy our company today again. Now, quantum technologies. We have all heard the word at some point, whether it's quantum leap, quantum computing, quantum sensing, you name it. But I'm pretty sure I'm not the only one here with the audience not exactly knowing what we're talking about. So that is what we're here to discuss today, what is quantum, what are quantum technologies, what is their span, how far along are we with these quantum technologies, and also, and just as importantly, how these are going to be helping or already helping our navies around the world. And to do this, as always, I am surrounded by a great panel of experts, and I'm also very happy to say that we are all doctors today. Permanent head damage, as we used to say when I was doing my PhD. So it should be a very interesting roundtable as usual. So without further ado, I would like to introduce our speakers to you today, and I will start with Sylvain Schwartz, who is quantum physicist at ONERA, which is the French Aerospace Lab, and if I'm not mistaken, at ONERA you have your own dedicated quantum lab.
Absolutely, yes. Good afternoon, and thanks for the invitation.
Thanks very much for coming. And then here to my left, I also have Myriam NOUVEL, who is quantum project leader at THALES. Welcome, Myriam.
Thank you, Alix, and hi, and good afternoon to everybody.
It's a pleasure to have you here. And finally, last but definitely not least, Cédric Tavernier, expert in cryptology at HENSOLDT France. Hi, Cédric.
Thank you very much. Good afternoon.
So before diving in, I would like to remind our audience that this is a live event, that this is an interactive event. So should you want to ask any question to our speakers, please do so through the platform that you're using to watch this event. And I will get them in the little screen that I have here, and I will ask them as I see fit during our conversation here today. And now I would like to get into the heart of the matter, and I will start with you, Sylvain. If you perhaps would like to give me also, a little bit of an introduction as to what we're talking about. What is quantum technologies?
Sure. So maybe let's start with what is quantum physics. So quantum physics is a theory that was established at the beginning of the 20th century by famous founding fathers like Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, many others, famous names. And initially, it was not meant to provide technology. It was an intellectual adventure to understand the laws of nature, of physics, at the microscopic scale. How does an atom behave, or a single electron? And so they developed laws for this, and the theory was very successful. It was confirmed by experiments. And in the second half of the 20th century, it led to a first batch of technologies that we can also call quantum technologies, but which are not the technologies we're going to talk about today. These are semiconductors, lasers, the atomic clocks, which are at the basis of GPS, and the nuclear magnetic resonance, which is used now in medical imaging. So all these are kind of first generations quantum technologies that radically changed the way we live in the second half of the 20th century. And today, we're at the advent of a new era, which we call the second quantum revolution. And the promise here is to develop new technologies beyond those semiconductors, lasers, and so on. And those new technologies, what they have in common is to be enabled by the possibility to control single particles at the single particle level. So now physicists are able to control a single atom. They are also able to build artificial atoms, for example, superconducting circuits or defects in diamonds, and to use these as elementary quantum devices. And this opens the door for new applications. The most famous one is quantum computing. If you encode calculations in this encode bits of information in these single atoms, or artificial atoms, and then you make them interact, you could in principle solve some algorithms much faster than a classical computer can do. So that's one of the promise, but it's not the only one. The second quantum revolution also includes quantum sensing, where we can use those individual quantum systems to perform new sensors with new possibilities that could change or have a strong impact in some applications, including the naval ones. And finally, a third, pillar of these quantum technologies is quantum security. If we encode the information, for example, in single grains of light, there is the promise to reach some unconditional security, where you can be sure that if somebody has spied on you, it will necessarily affect those elementary quantum systems, and so you can be sure at the end of sending your secure key, for example, that you have not been spied on. So that's basically the thing we're going to talk about today.
Right. I think someone was explaining that to me, in fact, the whole quantum encryption, that you have twins, and basically if you tweak with one of them, it will show on the other one. It's something like that, isn't it?
Exactly, yeah. You can create correlated pairs of particles, for example, photons, and if you encode information in that, you can definitely use that to transmit a secret key between two people, with a posteriori being 100% sure that you have not been spied. So it's a kind of unconditional security based on the quantum properties. The fact that if you make a measurement, you perturb the elementary particle, and so if the spy does so, then it will be detected at the end because he has perturbed the measurement.
Okay. Myriam, you wanted to add something?
Yes, just to add what about you said, Sylvain, maybe there is the first revolution, and the first revolution of quantum is nowadays everywhere for everybody. It's not magic. It's not. We can demystify these things. For example, you've got it in your mobile phone, your laptop. This is the semiconductors, as you say, based on very lighter or tiny components, a chip that's called transistors. And between the physics law and this in our nowadays, it took almost maybe 80 years. So between the fundamentals and the real application in our life, or also for naval or military application, it took a lot of time to do that. And there is another pillar. You mentioned the three classical one, computing. For the second revolution, of course, I'm talking about that. Computing, sensing, and secure communication. And you've got also all the what we call enabling technologies. That means the technologies that, thanks that you can, I would say that operate this quantum physics. For example, vacuum, cryogenics. And also lasers, in order to catch the atoms and the infinity tiny, tiny physics elements. So, for example, THALES, we have main assets and skills on these domains. So it's part of the game also, in order to have this second revolution in the nowadays operation or for the future.
So if I'm getting this right, now don't bite my head off if I don't, but effectively we're talking, it's the story of an atom. And then from there we have all these different applications according to what we're doing with this atom or these atoms. Is that right?
Right.
Yeah.
So it doesn't have to be an atom. So an atom is an example of an elementary quantum system. Yeah. If it's a two-level atom, people call it a qubit for a quantum bit of information.
That's where it comes from,
And then there are actually many different possible physical implementations of a qubit. Could be an atom, could be an artificial circuit, which is cooled down to cryogenic temperature. Could be a grain of light, a photon, can also be used as a qubit. Could be an ion, a charged atom. Could be a defect in a solid state matrix, like a diamond. So there are many, say, different physical implementations for those qubits, but they can all share in common the promises of those applications of the second quantum revolution.
Okay, okay. I think I get it. Yeah. So in terms of, to try and take this a step back and understand how this can be applied, as you mentioned already a few examples of the first revolution and how this is applied in our everyday lives. So perhaps, Sylvain, can you give us a bit of an example of the type of projects that you're working on at ONERA related to specifically defense?
Yeah, so for example, if you think about radio frequency detection, so typically what people would do classically is to use an antenna, so say a piece of metal, and when the wave comes it will induce a current which will be measured, and that's how you detect radio frequencies, or that's how your radio receiver works. And so at ONERA we're working on a project where the idea would be to replace those antennas with atoms.
Okay.
And it's a kind of a special atom that, well, it's not a special atom, it's an atom that we put in a special state, which we call the Rydberg atom. So basically the electron, which is around the nucleus in the atom, will be put with lasers far, far away at a very large distance from the nucleus compared to a ground state atom, which where the electron will be at a much shorter distance. And because the electron is far from the nucleus, this atom will act as a small dipole, and it will be very sensitive to an external radio frequency field that comes along. And so the idea will be to replace the antenna by a collection of atoms that we cool down with lasers, and then by looking at how the atoms are perturbed by the incoming field, we can learn some information on the incoming field. And this, in principle, could enable to perform very sensitive and accurate detections of radio frequency fields. So
we're talking electronic warfare here?
Yeah, for example, exactly.
Okay.
Detect a signal with a very high sensitivity. So this way you could be aware earlier that something is coming towards you because you detect it with a higher sensitivity than a classical antenna. So that would be an example of
so it's faster as well. It's a higher sensitivity, so you detect it faster. No,
it detects smaller signals, say, than a classical antenna. At least that's what we hope. Yeah.
Yes. Just to again to complement what when we are talking about sensing or sensors in generally, so as probably you know, THALES is a provider of many kind of sensors for naval operation, for example, sonar, radars, or electronic warfare, as you said. And these sensors, what they are doing, they are translate the signals of the threats. The signal could be electromagnetic or acoustics, as said Sylvain, and they are translate this into only an alert on a display for on the submarines or so on. So that's what we call sensors.
Yes.
It's not only the first step, which is the sensing of the waves, the signal waves. It's the sensing, the detection, the localization, and probably identification, classification. But that means operationally, sensors, this is the translation between these signals and only an alert, for example. And what is important to have in mind is that for that, what is really important for the operational is that the earlier or the better the range of the detection, I mean the distance between the threats and you, so the better it is, the warning is better. The warning is better, of course.
Exactly.
So how can quantum physics be better for that? Is like explained Sylvain, it's to be at the beginning more sensitive.
Yes.
So that's just to have in mind what it can, one can offer quantum technology for the sensing and the classical sensing. So it wasn't the example with the Rydberg atom, but probably, as you know, in Euronaval 2022, THALES won the Innovation Prize concerning superconductivity antenna. which is another principle of physics, which is conductivity. And the promise is to have a factor of between, I don't know, between 100 and more than 100 precision about this detection. So let's say that the operational time, so range
Yes.
is life, so it's very important to have this. And what is important also is that when you are talking frequency, that means the antenna of reception, classical one, the lower the frequency is, the higher is the size of the antenna.
Mm-hmm.
So, for example, you are operating, I don't know, about 100 megahertz. The antenna is 2 meters.
Mm-hmm, mm-hmm.
So to have an antenna or multiple antennas of 2 or 3 meters above, I don't know, helicopters and some marines, it takes place.
Yeah, yeah, yeah.
So you have to reduce the size only. So this is another advantage of quantum technology.
Reducing the size. Yeah.
Reduces the size.
Yeah. Okay. I will come back to you both, but I'd like to hear a little bit more from Cédric at this point. If you can tell us a bit about what you're working on at HENSOLDT.
In my field, our main concern is quantum computer. When this one will appear, the classical asymmetric cryptography will be broken.
Okay.
Then the challenge is today is to implement a new generation of algorithms which are resilient against quantum computer. We know that today with a quantum computer with that can handle a few thousand of qubits will be able to break absolutely every classical asymmetric cryptography. Fortunately, for 2 or 3 years now, the NIST launched an international competition to propose a new standard regarding asymmetric cryptography, and some signature and key encapsulation mechanism have appeared. And the challenge today for HENSOLDT and other organizations is to implement securely this kind of algorithm, especially to propose also an hybrid cryptography, because this new generation of cryptography is quite young, and the government are not fully confident in this new cryptography. So we have to manage both, and by proposing, for example, 2 signatures with 2 keys, and this is the challenge today.
So you're telling me that we're already with some progress with quantum computing,
Yes.
and we're already thinking ahead of this, wondering, okay, this is what it's going to be doing to cryptography, and this is what we have to already figure out now, how to keep our messages safe, basically.
Yes. Yes, of course, you have these 3 pillars of cryptography: confidentiality, integrity, availability, and even traceability. But clearly, when this computer will appear, for example, if your signature, your electronic signature, can be usurped by anyone owning this kind of computer. So this is why we work on.
Yes, this is computing. Quantum computing is an advantage for both of everybody here, but it's also a threat, as explained Cédric, a really threat concerning our algorithm of actual algorithm of cryptography, and that's why you mentioned the NIST and the way to test, and there is a program in which THALES is part, launched in the beginning of this year, an European program called Nostradamus, in which there will be the first infrastructure of testing this new kind of cryptography. So this is open to everybody who wants to test their algorithm in order to be more confident and to convince all the authorities concerning this first cryptography and first step of quantum key distribution.
Yeah. Yes, and HENSOLDT France also is involved and coordinate a huge project, X7 PQC, which is dedicated to adapt and to update the classical protocol to this kind of cryptography. So in this sense, it participates also to this kind of action. The challenge today is also to be resilient against physical attacks, in fact. It's not enough to have a strong algorithm theoretically. We need also that if an attacker has a physical access to a cryptographic equipment, that the implementation is enough resilient against an attack based on laser injection, a fault injection with a laser, against electromagnetic radiation and things like that.
So you've used a lot of big words. So let me take a step back. Like if I'm crew on a ship or somewhere in a command center, what does this mean for me, what you've just said? This is $1 million question.
It means that even if your algorithm is very strong, theoretically, it means that you need to do, for example, 2 to the power 128 elementary operations to break it. In fact, it's not enough. If you consider the context where an attacker has a physical access to the equipment, for example, to a VPN.
Okay.
Why? Because this guy can inject some fault inside your component, inside your ASIC, FPGA, and so on. He can also use the electromagnetic radiation coming from this component, the electric consumption coming also from this component, and he can reconstruct the key based on this data, in fact. And so this is very dangerous. And in HENSOLDT, one of our tasks is to implement it by implementing some countermeasures against this kind of attacks. This countermeasure already exists for classical cryptography. Mm-hmm. But this new cryptography, this post-quantum cryptography, is recent. And the challenge is to implement it with this kind of masking methods, this kind of countermeasure. And it's difficult because, of course, it makes the algorithm heavier in a sense that less efficient in terms of computation.
Mm. But we will have the quantum computing to do that.
During a period, probably during a certain period, we will live with both quantum computer and classical computer. And so.
Because you were saying at some point, and then I'll come back to you, Sylvain, I have more questions for you, but you were saying at some point that there's not enough trust yet or confidence in the system from some of the clients. Is that what you were saying, or did I misunderstand it?
Yes.
Yeah.
Maybe just to
yes.
say it again, or maybe differently, the cryptography is based on two stage or two steps, the key, mm-hmm. which is coded, mm-hmm. and the transmission and all the infrastructure and hardware, as you mentioned, and you have to secure both in order to use them. For the moment being, only the key are quantum, and what we call the first generation of quantum cryptography. And the second one, then the second stage, which is not mature at all for the moment, mm-hmm. is to have all the infrastructure also secured with quantum, if it's possible. And that is what we call post-cryptography.
Okay.
Post-cryptography. And if we do not have this for the moment, it's just, there is there is a point when the attack can be down.
Yeah, there's a gap, basically.
There's a gap,
yes.
Yes.
Did you want to add something, or?
Yes, it's exactly what you explained.
Yeah.
To give an example, without any countermeasure, you need a few seconds to reconstruct the key of such equipment.
Okay.
So
okay.
it's something serious.
So we need to make it hard. Yeah, yeah. Okay, I understand. Now, Sylvain, you were saying, what else are you working on at? Are you working also on quantum computing, or are you working on different things?
So we are working on quantum algorithms, not on the hardware, because there are already a very active ecosystem, including France. In France, to build quantum machines, so to try to make a quantum computer with all those different qubit technologies we talked. So some try with atoms, some try with photons, some try with superconducting qubits, etc. And we don't know if which technology will win in the end. And so many people are doing that, startups especially. And so at ONERA we are not in this race, but we are trying to find the need to do research on new algorithms, because those quantum computers, if they come to maturity someday, they will be very different from our classical computers, and including the way they will be programmed. So the actual vision is that they might replace or complement supercalculators that like professional use to perform some, hydrodynamic simulations or material or chemical simulations, rather than replace your personal laptop or computer. This is the current vision, and they will be programmed differently. So it's not enough to work on the hardware. You also need to find which kind of algorithms will be interesting for your applications to be implemented on those machines. So that's something we're working on at ONERA. And maybe to give another example of things we're working on, maybe in link with the theme of today about naval applications, I wanted to mention inertial navigation, which I think is something very important in this context, what quantum technologies can bring to naval applications. So inertial navigation is basically the way a ship or a vessel can locate itself on a map, basically without using an external reference like the GPS. So imagine you're in the middle of the ocean and you have no access to GPS. There could be many reasons for that. Then you still need to have something to locate yourself on the map. And the modern way to do that is called inertial navigation. So basically it consists of measuring the way you rotate and the way you accelerate, and then you integrate that on a computer. And so if you know where your starting point was, then from step to step, you can know where you are on the map. But the problem of that is that if there are some imperfections, for example, in your gyroscope, if it, has a bias of 1 degree, if it drifts over time, then your position, this will also integrate over time. And so after, 2 weeks of underwater navigation, for example, you can be very, very far off what your inertial navigation system tells you. And that's where quantum technologies could add something, because especially with atoms, again, you can perform very stable measurements of inertial forces, so accelerations and rotations, which are, say, calibrated with respect to the atoms itself. And because all atoms, for example, all rubidium atoms, because we're using rubidium, they're all the same. So it provides some kind of etalon for your measurement. You can always refer your measurement to those atoms. The same principle for clocks also. Atomic clocks use the same principle. And so this way, in principle, your quantum sensor will not drift, because it recalibrates itself on the atoms, which by definition...
It's a reference point, basically.
They do not change in time and in space. And so it's something where a lot of people, including my colleagues at THALES, but also at ONERA, we're working on, for example, atomic gyroscopes to be able to measure rotations using these self-calibration properties of the atoms to reduce the drifts and so to improve inertial navigation without GPS.
Okay. So I get that, for surface ships, for instance, there's a lot of discussions about GNSS denied environments, jamming and all sorts of things like this. But also referencing previous roundtables that we've had on uncrewed systems, is this something that can also help? I know that one of the biggest challenges for underwater systems is to be able to know exactly, as you were saying, where you are. because you can't use the GPS. So is this a technology that will also enable? Yeah.
Yes, of course. Yes, completely. And the challenge nowadays is to reduce the size of this, because, as I said, all our sensors are embedded on platforms. So you mentioned uncrewed vehicles, for example, but it could be also helicopters or buoy. So you need to have in mind that it's also a matter of have all the systems, not only the atomic parts, because in order to keep these atomic parts in the state of what we call cold atom, maybe we mentioned this, you need lasers. So the lasers have to be also very small and have a low, what we call a low swap, size and weight and power consumption, in order to be embedded. So that will be the challenges. And of course, it's very, as you mentioned, very important to have this underwater, because you do not have the GPS signals as references to navigate under the water.
Yeah, absolutely. Okay, so I'm thinking there might be people listening and wondering, I want that technology, it sounds amazing. How far along are we with this kind of technologies?
So it really depends on which technology we're talking about.
Okay.
So some quantum sensors are already, say, available or almost available. So at the stages of prototypes that have already demonstrated some quantum advantage, so some real usefulness. Some other technologies are less mature and are still at the stages of lab experiments. And so yeah, it really depends. But if I maybe wanted to draw a rough, tendency, I would say some quantum sensors are already quite mature. For example, accelerometers, atomic clocks, magnetometers with NV centers in diamond. So these are already working. Rydberg atoms for RF sensing is a bit in between, but it's quite mature also. And on the other, side of the technological readiness scale, you have the quantum computers, which have a very, very high promise, but which still need some developments to reach some, I would say, utility for the society. For now, they are solving algorithms which are kind of, serve as examples or benchmarks. But to my knowledge, no real problem so far is solved using a quantum computer faster than a classical computer. And of course, that would be a strong breakthrough. So a lot of people are working and investing money on that, but it's a bit on the low scale of technology readiness level for now. Yeah.
Also, Ministry of Defense is invest on this computing part, because probably, as you know, there is this Proxima program concerning computing, which was launched maybe 2 months ago, which is the course, say that, for between 5 companies in France concerning computing, in order to have maybe one quantum computer in, we don't know, I don't know, 10 years, 5 years or more. But it will not be accessible for everybody. So the first step is that it will be accessible to the Ministry of Defense, of course.
Yeah.
And concerning quantum communication, I think it is almost mature concerning the first stage, concerning the cryptography. But it's not at all for the second stage, because there are already live demonstration to have the
reference implementation already exists. For
What's
sure.
reference implementation?
Implementation of post-quantum cryptography already exists. You can find it on GitHub or almost everywhere. But I'm not sure that it's already implemented in all protocols, and that it is already implemented in classical VPN. It's absolutely not sure. But it exists, and it will be ready soon. It is on the way, I think.
With me.
So in terms of what you're working on at HENSOLDT, I know you can't go into the details, but
Yeah.
more generally speaking, what kind of timelines are we looking at?
We managed to finish this work in less than 3 years. So in less than 3 years, we should be able to encrypt, to sign with such algorithm.
But as you said, hybrid, that will be the end of the period with the hybrid methods, or we will still be working with the hybrid methods that you were talking
With an hybrid method.
Yeah.
Yes, it's a question of confidence because this kind of algorithm is quite recent. It's not, we have not enough experience. The researcher need to analyze, need to try to break it before being completely confident in it.
Okay.
Yes.
So I know we were talking about this earlier on before coming online. What I'm intrigued about as well is I very openly admitted when I started this session that I'm very out of my comfort zone here. I'm wondering if your customers, are interested in this, are asking questions about these technologies, are wondering, are eager to see it happen.
Yes, for sure. They are afraid about the coming. Yes. The coming of the quantum computer, and they request mandatory that we provide this hybrid cryptography.
Okay.
It's something very important for them.
Okay.
For sure.
There's eagerness to see this happen. What about you, Myriam?
Yes, I would say the same, maybe a point concerning the quantum computing. Probably we are in the same end as I have a comparison with artificial intelligence. We are now in the same wave than maybe 3 or 4 years before for the intelligence artificial. As I said at the beginning, we have to demystify this and just to be sure that not to be afraid, just to say that don't be afraid, to explain and to explain how it can be, it can add value in the naval operation. You mentioned the GPS denied navigation, and also maybe I can have another example, for example, a concrete example, because we are here to speak about concrete application. For the moment being, the maritime patrol aircraft, they have to fly very low above the sea, which is dangerous because sometimes the sea stays very high and it can be dangerous because they do not have the sensor that have the range enough to detect where there is a threat or not. And with this new quantum sensing, as I said before, they can offer these capabilities. And it's not so far enough, as you said, some kind of technology based on different physics will be available, are already available for the navigation, but for the more sensing, as I have to say, that means locating the threats, it will take almost maybe 3 or 4 years. My opinion, it's only my opinions, to have this in test and aboard some aircraft or ships.
So when we're talking maritime patrol aircrafts, are you detecting threats? Are we talking about potentially detecting the submarine, which is at Perco? So it would be something that would be complementing with the magnetic anomaly.
Of course, yes,
detector?
which is limited for the launch detection for the moment being.
Yeah.
So we want to increase this,
Yeah.
as I said, because we want a warning as soon as possible, of course.
Absolutely. So this is something, because at this point in time, obviously, it's being used once there's almost like a sure contact, knowing that there's a submarine somewhere. So this is something that could be used perhaps more, as you said, longer ranges.
Of course, this is the promise, and we have to test this, definitely.
Okay, okay.
About magnetic anomaly detection,
Detectors,
actually quantum technologies could also help in this domain, because with these quantum systems you can also sense magnetic fields with a high sensitivity. They are different, again, physical technologies to do that based on quantum technology. And yeah, so that could be also an application of quantum technologies, magnetic sensing and magnetic navigation also perhaps. It can also might help also to know the magnetic field
true.
as an extra information where you want to know where you are on the map.
Yes,
So that's, magnetic detectors are also one promise of quantum technologies.
Yeah.
yes, but the threats that we are looking for, they are using countermeasurement.
Of course.
So you have to have this in mind also, in order to be sure that it could be detecting or not. So
you have to be
yes.
one step ahead.
Yes, right.
As is often the case, exactly.
Yes, in military application, of course.
So what about you? I mean, I don't know if at ONERA you are, in touch with customers, with potentially defense customers.
We're a public institution, so
Yeah.
we don't have customers per se, but we have contracts with industrial partners. Of course, we're here to help them. And what I noticed is a strong interest of almost all major, industrial players for quantum computing. So either they're afraid of it or they're just curious about it. What could it bring to my business and so on. So my impression is that now in almost every company of a certain size, there are a few people or a small group dedicated to just watching how this technology develops, start to think about which algorithms they could use for their business. So I would say everyone is curious about that.
How it will
Yes.
develop. Yeah.
Yes, yes.
Yeah. So we've talked about radars, we've talked about maritime patrol aircrafts, we've talked about computers. What about, can it also help submarines? Can it also do something in terms of discretion, detection, things like that, or not yet? I'm just throwing this there. You might be telling me that no, it's not the case.
Sorry, go ahead.
As far as I know, for the because this what you say, it's something to react, as you said, or something like that. For the quantum sensing, for the moment being, they are only receive. So you can't jam your enemy. So that's the limitation.
Yeah. Okay. Sylvain, you were going to say something?
Well, to me, the two main applications for submarines are those we have already talked about. So inertial navigation. If you put quantum sensors in there, of course, they already have gyroscopes and accelerometers, but if you add on top of that quantum gyroscopes and quantum accelerometers, then you might reduce the drift and improve the precision of the navigation. So that's definitely one big application. And the other is probably, to me, magnetic anomaly detection that could be used maybe against them.
Against it, exactly, yes.
So that could be enhanced by some quantum sensors. So that's the two main applications for submarines, I would say.
Okay, well, still pretty interesting. So in terms of where we're going with all this, we've already started touching on the subject of how far along we are and, certain gaps. You were mentioning gaps earlier on that could be exploited before. So maybe if you'd like to start, Cédric, so what can we be looking forward to in the next few years, the next advances in terms of post-cryptography, in terms of computing? What you're looking at HENSOLDT? What's your next challenge? What keeps you up at night? Other than being here at this roundtable.
Maybe we can try to attack this new generation of algorithm. To build it, mainly they use one kind of mathematics. They use lattice, and maybe this is a weakness of this kind of cryptography. So it would be interesting to invest in attacks regarding this, because it's not enough to base the whole cryptography on one kind of mathematics. This is what I can see. Regarding the symmetric cryptography, for example, for submarine, how to communicate with submarine, nothing is really new in a sense that you just need to multiply the key by 2 in order to be resilient against a quantum computer. So
Okay.
nothing new regarding this.
Myriam, did you want to add?
I think the challenges is, as I say, the classical sensor is not only the first part, the sensing of the waves or the signal of the switch, but only all the system. So and all these systems have to be compact. So the major is to have more compact as possible quantum sensing for the naval application, and the other step is to have this secure infrastructure in order to have the post-quantum cryptation and to be able to have all this, and not only hybrid, as you said, to have all this system. This is the two major for THALES
That's keeping me
points.
up at night.
Yes.
Okay. What about you, Sylvain? Many things.
Yeah. So I kind of strongly agree with Myriam about this very important aspect of getting things more and more compact. Because for now, even if we're talking about elementary particles like an atom, to manipulate the atom, you need a huge, well, not huge, but a kind of reasonably big rack full of electronics, of lasers, and then you send that with optical fibers or microwave cables to a vacuum chamber where your atoms are. And so it's sufficiently compact to be put on board, I don't know, a submarine or an aircraft. But of course, if you could get that smaller and smaller, we could reach more and more applications. I don't know, something that could be carried by a single person, or well, not go into our smartphone yet. That's probably too far of a vision. But there are definitely things to win in terms of size, and that's something very, very important to me. And then beyond that, it's just also finding new architectures about how to handle those quantum systems. You mentioned initially that we could create strong correlations between pairs. Actually, there's a more futuristic, a way of using that would be to improve the sensitivity of the measurement by creating quantum correlations between atoms or qubits. So if you use independent atoms, you can reach a certain precision, which is, sorry if I'm a bit too technical, but it's like the precision will be 1 over the square root of the number of atoms you are using. And if you now use a quantum state, which is where you have these strong correlations between the atoms, in principle you could have a precision scaling like 1 over n. So you gain between 1 over square root of n and 1 over n. You gain, for example, if you have 1 million atom, you gain a factor 1,000 on the precision. So that would be a next step to improve even more the sensitivity of those quantum sensors, would be to use not independent individual particles, but strongly correlated states where many atoms are what we call entangled, as for those pairs of photons you mentioned initially. And so this already exists in academic labs. It's even used for one application, which are the Virgo, the gravitational wave detectors, which are those big interferometers you can find in Italy or in the US to detect gravitational waves. So it's a scientific application. When a gravitational wave passes by, it changes the length of 2 very long arms of an interferometer with lasers. And they actually use those entangled states of light to improve the sensitivity. So if we could transpose those techniques to gyroscopes or gravimeters or RF sensors, then we could gain more on the sensitivity. But those states are also very fragile. The same kind of states you would use in a quantum computer. It's what makes also quantum computing very hard. But if we can do that for quantum computing, we could also probably do that for quantum sensing and enhance even more the sensitivity of quantum sensors. So definitely a motivation to
So,
stay up at night.
so if I'm extracting from what you're saying, we're talking about increasing precision.
Yes.
We're talking about also, as also Myriam was saying, decreasing the swap, which is something that is keeping naval architects up at night, obviously, because we want to add more and more systems on those ships to be able to have more early warning, and therefore, if we can save space, that would make everyone happy. So these are the two main aspects that we're really thinking of. Okay.
Yeah.
Myriam, did you want to add something?
No, it's okay.
Okay, well, I think I have gone through most of the questions I had for you, but perhaps there is something that I haven't asked that you wanted to add in terms of where we're going with all this, or any programs that you're working on in your companies.
So just to keep in mind, because of course precision and so on, but we have to just put in mind that, as I mentioned before, for the classical sensor, for example, or classical cryptography and so on, there is an end user which is, military, and the only thing is, it's for him, it works, and it have the good information with the early warning, as we are saying. So we need to, in order not to be afraid, as you said, explain and explain again, and that it's cool. These talks, for example, just to give the opportunity to say that it's not magic, that it will probably works. For most of what we say, we have to wait for the end of the programs, different programs, and evaluation, testing in real condition, harsh condition also, on the vessel or aircraft, for example. So just to have this in mind, quantum is not magic, and quantum has to fit with operational needs, definitely.
Yes, I think, and you're right, you were mentioning, a parallel with artificial intelligence earlier on, and this is something that is keeping a lot of people up at night in terms of trying to make this transparent, understandable, explainable, and making sure that people understand what we're talking about. And as it's not magic, it's not witchcraft, it is physics, and we're doing something that is going to help and supports the war fighters of tomorrow, rather than just scare them away.
And probably, I don't know, in 50 years later, we will be like now. We say we've got physics, quantum physics in our pocket with the mobile phone. So maybe in 50 years we have the same with this second quantum revolution.
Absolutely. Cédric, did you want to have one last word?
No, maybe one thing. When we talk about a quantum computer, of course, we talk about a capacity of computation, but we do not talk about memory.
Okay.
But I'm not sure that quantum computer brings something regarding the memory. And for example, for cryptographic, post-quantum cryptographic algorithms, the main problem is the size of keys, which is considerably larger than for classic cryptography. So I don't know if the specialists of quantum computer and physics, they think about this kind of progress, or I don't know.
Yeah, so there are even a startup in France which is called WeLink, which is dedicated to building quantum memories. So that's a fact. Then how exactly this is going to be used with quantum computers is not totally clear with me. Those quantum memories are also useful for quantum communications, where you want to store a quantum state to wait for another to arrive so that they can interact and go on. But they might also be useful for quantum computers. But also, again, you have to think about you have to keep in mind that this quantum computer will be radically different from a classical computers, and so maybe these notions of memories, of random access memory, etc., will be difficult to transpose. Yeah. So it's
different in terms of hardware, because you were mentioning software,
yes,
everything.
No, the hardware is radically different.
We wipe out the image of a computer that we have today, and it could be looking something different.
Even the qubit itself could be used as a memory if it keeps the information for some time. Then you could call it a quantum memory. So I think it's a bit hard to transpose, every piece of a classical computer to a counterpart in the quantum computer. They're radically different.
So we talk about, I know this is something I write about a lot as well, so it may be a bit of a conceptual question, so bear with me. But, we talk about evolutions and revolutions, evolutions being just improving on something that already exists. And the sense I get, without wanting to make a pun, but the sense I get from quantum is that in some aspects, possibly computing and cryptography, it could be a revolution as well in the way that defense capabilities and systems are built and developed. Could that be correct?
To me, as a true revolution is the fact that people are not able to manipulate individual elementary particles one by one. And when you look at what the founding fathers wrote, for example, Schrödinger, he thought this would never be possible. There's a famous sentence like it's more plausible to have a dinosaur in a zoo than to have a single particle which could be controlled by in an experiment. And now it's a reality, and I think that is a true revolution. Now, whether it's gonna induce or you want to call the technological applications a revolution is it's a conceptual question. I think a working or useful quantum computer would definitely be a revolution because the promise are really huge. About those quantum sensing, it's not a revolution, but it enables new applications. They can be useful if your sensor doesn't drift. Well, it's better than if it does drift. So it's either you create an evolution or a revolution, but at least there are new applications which are around the corner, which are in the short term.
Which we can look forward to. Yes. Myriam, did you want to add something?
Yes, you're right. Maybe it's for some people it's not really a revolution. It could be because the improvement for the classical sensing, for example, is only 10% of evolutions, but things through this more precise and maybe a new utilization or new concept of operation. This could be a revolution. So that's why we say revolution, and maybe it is inside a revolution because we do not have all the key of what it will be in 10 years or 3 years. So that's why we called about revolution.
Yeah, makes
and
sense.
not evolution.
Cédric, did you want to add something?
It is a kind of revolution in cryptography, in a sense that, as Sylvain said at the beginning, you can build a shared secret, a mutual shared secret between two parties just by using the property of qubits, where before we needed to use the Diffie-Hellman protocols, for example. So Diffie-Hellman protocols is mathematical protocols which is very useful to build a common secret between parties.
Okay.
And it's it can be completely replaced by this kind of communication.
But practically, what would this mean for me?
I will try to not be too long. In fact, when you want to cipher a huge quantity of data, voice, for example, you use a symmetric cryptography. But symmetric cryptography, you have not this private and associate public key. You need to be agree with your partner on a common secret.
Okay.
And in fact, in classical VPN, for example, there exists some protocol, which is named Diffie-Hellman protocol, based on asymmetric cryptography that allow to build this shared secret.
Without having agreed ahead of time?
Yes.
Okay.
But in this sense, it can be completely replaced. And it will not be useful if this kind of of technology appear. And I think it exists already, this kind of communication. I mean, you can exchange some...
Yes. Quantum
Even
key
all
distribution.
technology,
Yes.
yes.
You can,
And
yes.
if someone
years ago.
observes, it will be detected. Yes.
Yeah, there was also a satellite by China.
China in
A few years
2000.
ago that established a secure communication between two cities in China using a satellite as an intermediate relay, secured by quantumness. So this is a reality. Yes.
Okay.
So this is a revolution.
This is a revolution. Well, I actually have one question from the audience to conclude actually our talk today. And it's, are there country regions that are more ahead than others in terms of quantum key distribution?
What is the question exactly? What is
If there are regions or countries that are more ahead in terms of quantum key
Yes,
distribution?
I think China definitely
China.
led the race, or at least was leading the race 3 years ago when they announced this satellite. Before China, it was Switzerland. There was a famous professor called Nicolas Gisin at the University of Geneva, who was a pioneer who did the first demonstration between, I guess, banks in Switzerland that could exchange information secured by quantum communications. And then I guess THALES made
Yes, and there is
that.
there is this European consortium, as I mentioned before, that contracting this program, Nostradamus and other programs, of course, which is led by what we call QCI for Quantum Communication Initiative.
Okay.
In order that, yes, I think that for the moment being, almost all major countries in the world have their what we call national investment concerning quantum, and France is has a lot of investment, and we are not in the background. I mean, it's from my point of view, and also concerning the European, and we have now, yes, everything we can have in investment in order to not to be in the background. So Chinese, of course, it was the first experimentation was in 2000. I think it was in 2017. But since
We've been
Europe, yes, Europe filled the gap.
Our projects of quantum satellites under
So
the
there is,
European Union,
yes.
but it's where we
And Nostradamus is with
working.
satellites also. So.
Okay, all right. Well, as I've promised, the hour goes really, really fast. So thank you very much again for being with me today. It's been a pleasure having you here at this roundtable and learning more about quantum technologies. And I hope it was the same for our audience, definitely. And I would like to remind everyone that the next Euronaval trade show will take place this year in Paris, from the 4th to the 8th of November. So we're hoping that you will be joining us. There will be, I'm sure, many announcements from different companies, so we're all looking forward to that. This concludes our 5th and final roundtable before the show. But during the trade show, we will have other roundtables in the center of the show, along with workshops and along with many other projects that we're working on. So thank you very much again for being with us today. Thank you for being here today.
Thank you.
Thank you, Alix.
It's been a pleasure, and we look forward to seeing you in November. Thanks.
Thanks.
Thanks.